Hey there, in this video I want to talk about the Runge Kutta method. I guess I really should say Runge Kutta methods. They're a whole family of methods, although when we say Runge Kutta we usually mean the fourth order Runge Kutta. There are lower order Runge Kuttas, there's a first order Runge Kutta, and that's exactly the same thing as Euler's method. We'll also talk about the second order Runge Kutta, which is sometimes called the midpoint method. So here's the idea. With Euler's method, let's say we have some dx dt equals some function of x and t. And in effect, what we're trying to do with Euler's method is for some starting point x of t, is we're extrapolating outwards by the derivative there, the slope, and we're finding then some new point x at t plus h, where h is our step size. So, I mean, I drew this exaggerated from what you would ever actually do with Euler's method, but the point being that there is some inaccuracy here caused by the fact that the slope changes. And in fact, if we think about our picture here, if we had used a different slope, in particular, if we use the midpoint, we'd almost always be better. This is kind of like when we talked about derivatives. If we use the midpoint slope, which is a little bit more shallow, and we try to go parallel to that, we'd actually get a lot closer for a case like this. So our midpoint slope is better. And to prove why it's better, what we can do is a Taylor expansion, which is what Euler's method's based on. Euler's methods do the first extra term in the Taylor expansion, the derivative term. So let's look at the Taylor expanding using the midpoint. Okay, so if I go forward to t plus h using the midpoint, then that value to 0th order would be the midpoint. To first order would be the midpoint plus an extra dx dt times h, and well, 1/2 h, because we're halfway there already, where that derivative is evaluated at the midpoint. And then we would have the second order, it would be a 1/8 h squared d2x dt squared. So these are just terms out of the Taylor expansion. And of course, this is an infinite series, but that's enough for illustration. Likewise, from the midpoint, we could take a step backwards, which would actually put us at our starting point. And that would then, to 0th order, again, be the midpoint, but the idea being that it would be more accurate to say it's the midpoint minus a 1/2 h step backwards using the derivative at the midpoint. It's going to be a plus here, so alternating pluses and minuses throughout this particular series as we go backwards. T plus 1/2 h, and then so on. And so the idea here is, well, what if we took x at t plus h and subtracted x at t? Well, what's going to happen if we do that subtraction is we're going to get some cancellations. We're going to find that the midpoint term would cancel out, the second order term would cancel out, all the even powered terms are going to cancel out. But what's left then is going to be an h dx dt at the midpoint, and then plus whatever's left is going to be third order. So it would be like order powers of h to the third power. So that's now a second order method. We're accurate up to second order. Our errors are third order. And so, I mean, if we look at this and we rewrite it, this is saying that x at t plus h is equal to x at t. Go forward using the slope at the midpoint instead of the slope at the starting point. I mean, that's exactly what I sketched up above with Euler's method. So up here, this picture is the same thing as this statement down here. Okay, so great. How do we find the midpoint, though? So our dx dt at t plus 1/2 h, we can find that using that dx dt is by definition here f, and I want to evaluate f at x, looking a little bit ahead in x, and then using t plus 1/2 h. So plugging values into f is not a problem because we have f as a function. What I don't have is what x is there at the midpoint, like what is the midpoint x? And so what we're going to do here is we're going to have to calculate that using something we already know, which is Euler's method. So calculating with Euler's method says that to find x at the midpoint, what we do, or approximately what we approximate, is we take x, and onto that we add 1/2 h times f using the starting point. All right, and you might worry a little bit about, like, has this thrown away all the advantage? We had something second order, but now we have to do this like first order step. And if we look at what kind of error this introduces and we Taylor expand it out, it's going to take a while, so I'm not going to do it in this video. But if we did that, we would find that, yes, it adds error, but it's a third order error. It's no worse than what we have with the midpoint method. So we actually do have an improvement doing this. Because this is not our solution, but this is just a step on the way to our solution. If we put all this together, we have what's called the second order Runge Kutta. Also called the midpoint rule because we're finding the midpoint. The basic algorithm is you calculate an intermediate value k1, which is equal to h times f of x and t. You calculate another value k2, which is equal to h times f at x plus 1/2 k1. So this is like finding that midpoint. K1 is like k1 is a full step, and then half of that is the midpoint. And then for time, we'd have to also go half a step forward in time. And then our answer, our x at t plus h, is going to be equal to the original x at t plus that k2. Okay, but we can use this idea, the idea of finding the slope at different points, as a way to improve the accuracy. And in fact, even better than just doing the midpoint would be doing several points in between and averaging them in a weighted sort of way. That would, if we pick just the right points and just the right weighting, we should be able to remove even higher orders out of the Taylor expansion. The price is we just need more steps. And the sort of sweet spot you reach is the fourth order Runge Kutta. Nothing stops you in principle from going higher order, but the equations start getting longer, and at some point it takes longer for your computer to evaluate all of the intermediate calculations than the time you'd save using a simpler method with just more time steps. So this is really our sweet spot for solving ordinary differential equations. So first thing we're going to do is we're going to take a full step to get a value k1. And then from that, we're going to calculate an intermediate value k2. This one's based on a half step. So we'll go x plus 1/2 k1. So we've estimated what the midpoint is. And then we're going to do t half a step ahead to match. And then we're going to calculate a somewhat better, estimate k3. Same kind of idea, where we go a half a step ahead, but now we're going to use k2. t plus 1/2 h. And then we're going to do a full step. This is called k4, where we go x plus all of k3, and then t plus all of h. And then we're going to average them. So to find a full step ahead, what your new value of x is, you start with your original x, and then onto it you add a weighted average. So there's a 1/6 here, k1 plus 2k2 plus 2k3 plus k4. And if you're wondering, like, where do these numbers come from, like the 2s and the 6, where do they come from? They are there to make the higher order terms disappear out of the Taylor expansion. And so it would be kind of tedious, but I mean, from this you could work backwards and see how it worked out and why those are the right values. But nonetheless, these are your ideal values, and this is sort of like one of your most famous computational algorithms here. It solves ordinary differential equations for you. It's pretty quick to code. In fact, I'll do that in just a moment. And it's accurate. It's super accurate. So you'll see that when we try it out. Something that was just kind of okay with Euler's method, it looks beautiful when we try it with Runge Kutta. So here we are back in the notebook. I want to try an example problem. We're going to do the same example that you did with Euler's method. dx dt equals x cosine t. We're going to do the same initial conditions. X at time 0 equals 1. And we're going to use the same step size, which was pi on 10. And I want to show you that this method's a lot more accurate than Euler's method. Now, before you move on, you should actually pause this video and complete the exercise down below where you write the function RK4. And the call signature that I'm going to use for that is it's given a function, an initial x, an initial time value, and a step size h. And then its job is to return x at time t plus h. So you need to write that function. I'm going to use it in here. So go ahead, pause the video, go do that, and then come back. All right, so welcome back. So I'm going to assume that you already have that defined. I've already typed that in a cell that I've since deleted, but it should be loaded in my notebook. And now let's write the code to solve this differential equation. First thing I'm going to need to do is define f, the function of x in time. And so it's a one-liner here. We're just going to return x times cosine t. I need to set a value for h. Just so we're matching the previous problem, we're going to set that to pi on 10, which is actually a pretty large step size, but we'll see it works out anyway for us. Our t values are going to be an array created with a range, and you might already have this array defined in your notebook, but just in case you don't, that was 0 to pi, and we were taking step size h. And our x values start as an empty list. Now we're going to run through a for loop for every time in the time value array, starting with our initial condition, which is x equals 0, and then for t in t values. First thing we want to do is append the previous value of x into the list x values. So we're going to append in x, so it's going to start by appending the initial condition, and then as we go, it'll append the new values in there. And then we want to update x. And so this is where the Runge Kutta method goes. Now, rather than type it out every time, since it is such a common method, I sort of want to encourage you to write a function for it that does a single step of the Runge Kutta method, and then plug that in here. Okay, so this is from the try it that's down below. Okay, so you need that code for this to run for you. And now let's make some plots. I want to check how accurate my result is. So I'm going to create some exact values here. We're going to do a linspace 0 to 2 pi. And we'll take a whole bunch of steps. Oops, np.pi. So we'll do 100 steps. This particular differential equation has an analytic solution, which you should have worked out in an earlier assignment. The answer, or the analytic solution, is e to the sine t. So in this case, we'll make t exact. So for all the time values, we'll get an array of x values. And we'll plot t exact and x exact. We'll let that be a line. So that's just for comparison. And now let's look at what our Runge Kutta code calculated for us by plotting the t values and the x values. We'll use dots for that, and there'll be a lot less of these because with pi on 10 we'll only have 20 dots. Okay, let's see if this works for us. Oh, look at that, it's beautiful. So our dots are like exactly, or not exactly, but really, really close to being on the line. Even though we had pretty big step size, this method is really accurate. It's a fourth order method. So this is what makes it the go-to differential equation solver, or ordinary differential equation solver, is that it is high accuracy for modest step size. It's fast. Now there are ways to break it. We'll learn about those eventually. But for most cases, this is going to work for us really well.